Welcome back to Upgrade to General, a series to help you upgrade your amateur radio license to General class. This episode is Subelement G9, Question Group C, and I'm your host, Ron Call, KE7CR. This question set is about antennas and feed lines, specifically directional antennas. So let's start with the first question. Which of the following would increase the bandwidth of a Yagi antenna? Most common directional antenna used in amateur radio work is the Yagi. The thing you need to know about any antenna is the larger the diameter of the radiating elements, the larger the bandwidth. So that same would be true of a Yagi antenna. So the answer is larger diameter elements. The next question asks, what is the approximate length of the driven element of a Yagi antenna? The driven element is a half wavelength. The next question, how do the lengths of a 3-element Yagi reflector and director compare to that of the driven element? Well, the reflector is going to be longer and the directors are going to be shorter. The idea is that radio waves radiate off the driven element, and because of the correct spacing, the distance between them, waves will reflect off the reflector and reinforce the waves from the driven element, so it increases the directionality of the wave going that direction. The directors focus the waves heading that direction towards the director, and so between the reflectors and directors, it helps to concentrate the wavefront in that direction. That's why it's a directional antenna. So the answer to this question is the reflector is longer and the director is shorter. The next question is, how does antenna gain in dBi compared to the gain stated in dBd for the same antenna? dBi stands for decibels in reference to an isotropic antenna. Isotropic antennas are not real. They're a fictional imaginary antenna. Think of it as a single point in space. You can't build an antenna as a single point, but mathematically you can compute the waves would radiate as a perfect sphere from an isotropic radiator, a single point. So you can compare the performance of a real antenna to a single point. dBd stands for decibels compared to a reference dipole antenna. It turns out that any antenna is going to have better gain than an isotropic antenna in some direction, any real antenna. For example, a dipole will radiate in a figure-8 pattern perpendicular to the dipole, so it's going to have gain in that direction. Compared to an isotropic antenna, a dipole has a gain of 2.15 dB. The question says, how does the antenna gain in dBi compare to the gain stated in dBd? Well, the gain in dBi is going to be 2.15 dB higher than if you stated it in dBd. So say you had a Yagi and they had a gain of 1 dBd, that's in reference to a reference dipole. That means it's a stronger gain than a dipole, while the dipole has more gain than the imaginary isotropic antenna, dBi. So if the gain over dBi is 2.15 and the gain over the dipole is 1, then the total gain would be 3.15 when you compare your Yagi to an isotropic antenna, but only a gain of 1 when compared to the dipole antenna. So when you state the gain in terms of dBi, it's always going to be 2.15 dB higher than when you state it in dBd. So that's the answer to this question. It's also why if you want to make your antenna sound really good, like it's got a lot of gain, they'll advertise it in reference to dBi because it gives you a higher number. Makes it seem like it's doing better. The next question is, what is the primary effect of increasing boom length and adding directors to a Yagi antenna? Well, if you make a longer boom, add more directors, you're going to increase the gain. So the answer is the gain increases. The next question asks, what does front-to-back ratio mean in reference to a Yagi antenna? So again, at Yagi, a directional antenna, you're comparing the radiation pattern, how much power you get in a certain direction compared to the other direction. So this is a directionality plot for a Yagi antenna radiation pattern. The red lines indicate the horizontal plane and the blue lines the vertical plane, and it's showing how the majority of the radiation is directed out in this direction. Now, a little bit of radiation goes the opposite direction, and you get some side lobes as well. So front-to-back ratio means how much power in the forward direction, these lobes, compared to power radiated in the opposite direction in this minor lobe. So the answer is the power radiated in the major lobe compared to that in the opposite direction. The next question asks, what is meant by the main lobe of a directive antenna? And the answer is the direction of maximum radiated field strength from the antenna. As shown in this diagram, it would be these lobes. They're the maximum radiated field strength. The next question asks, in free space, how does the gain of two 3-element horizontally polarized Yagi antennas spaced vertically 1/2 wavelength apart compared to the gain of a single 3-element Yagi? So they're describing 3-element Yagis, 2 of them, and stacking one on top of the other vertically, a 1/2 wavelength apart. What that's going to do is you're essentially doubling the effectiveness of a single Yagi antenna. Well, that's going to be double the gain. So the answer is approximately 3 dB higher. Remember, 3 dB is double the power. The next question asks, which of the following can be adjusted to optimize forward gain, front to back ratio, or SWR bandwidth of a Yagi antenna? A Yagi antenna is a directional antenna. It's got a driven element, a reflector, and then one or more directors. And the important thing is the distance, the spacing distance between the elements. If the distance is not right, the waves reflecting off the reflector won't reinforce the waves from the driven element. They'll interfere and cancel. So you got to get the spacing right. Same with the directors. So the choices here, the physical length of the boom, well, yeah, if it's not the right length, you're not going to be able to space the elements correctly, so that would be a problem. So if you adjust the physical length of the boom, then that could increase the front to back ratio or the gain, any of those. Then another choice is the number of elements on the boom. Yeah, if you add more directors, you're going to optimize the forward gain and the front to back ratio. Another choice is the spacing of each element along the boom. Yeah, again, you need to get those spaced correctly so you can optimize those. So the answer for this question is all of these choices are correct. The next question says, what is a beta or hairpin match? This illustration shows a hairpin match. What I have is a tape measure Yagi antenna for 2 meters that I used with my students for fox hunting, radio direction finding unit we were doing. And what this shows is the feed line, little coaxial feed line, soldered to the 2 different elements, connected with a hairpin. The answer to this question for what is a beta or hairpin match is a shorted transmission line stub placed at the feed point of a Yagi antenna to provide impedance matching. You can see how it's shorted because the center conductor line is soldered to the hairpin turn, which is soldered to the shield on the coax. So it shorts the coax, but they're connected, each half of the hairpin is connected to the opposite sides of the driven elements. So it works to adjust the impedance, matching the impedance from the transmission line to the antenna. So that's the answer to this question, a shorted transmission line stub placed at the feed point of a Yagi antenna to provide impedance matching. The last question says, which of the following is a characteristic of using a gamma match with a Yagi antenna? Now a gamma match, you see one in this illustration. This is another directional antenna. This is an arrow antenna I used for 2 meters for working satellites. What you see on this illustration, the feed line or transmission line attaches to the driven element. There's a short little stub that reaches down, this little short stub here in parallel with the driven element, and then branches over and attaches to the driven element with a connection there. This is called a gamma match. And what it is it adjusts the inductance or capacitance, the inductive reactance or capacitive reactance of the antenna to the feed line so that you get that match. The answer to this question is it does not require the driven element to be insulated from the boom. Notice how this driven element is actually touching the boom, and we can adjust the impedance using that gamma match. So that's the end of this question set, and we're almost done with the entire question pool. Hopefully this helped you learn some things about directional Yagi antennas, and look forward to seeing you in the next question set. 73, this is KE7CR.